So now let's talk about transparency. As you might imagine, if we go to the transparency section and we say 1, we have transparency. However, there are a few things that you ought to know whenever working with transparent materials. The first thing is ray limitations. So basically put, the general basics of rendering, rays get sent from the camera, they hit objects, and they're there to figure stuff out, right? Well, if we hover over this viewport as we're rendering and we press D, you'll find a bunch of hidden render options with Karma. You're not going to find these limits here with the actual Karma render settings down here. I imagine in the future that might change. However, we have this section here called reflection limits, refraction limits, and these are very important to set whenever you're working with transparent materials. To quickly demonstrate this, I have 3 spheres. They all live within one another. And right now we have an issue where this is rendering out black. And so anytime you see this weird black issue with refractive surfaces, that means your limits are probably not set correctly. So D for display. Here we have our refraction limits. And by the way, refraction means the same thing as transparency. You'll hear render engines use those two terms interchangeably. So just in case you're confused by that, that's what that's talking about. The refraction limit right now is 2. And the rule of thumb here is that with every single surface, you need 2 of these limits. So we have 3 spheres. That means 2, 4, 6. If I put 6, we can now see through all the spheres and it works just fine. If I'm at 4, as you can see, we've made it through the first 2 spheres, but the third sphere isn't showing through. So whenever you're working with refraction, take a look at the areas where glass overlaps the most, and then just count up the number of limits you need and use only that. This is a very expensive render option to set, meaning that it's going to impact your render times a lot. So only use what you need with this refraction limit. Now here's something interesting. We have ShaderBot, and you'll notice that a lot of areas are black. So you might think, okay, well, that must mean we don't have enough refraction limits going on. But even if I turn this way up to, let's say, 20, you never want to go that high, by the way. But let's say it's at 20, it's not making any difference for these black areas. And so another thing that can cause these black zones to happen is due to the reflection limit right here. So let's set this refraction limit to something else. I'm going to say 6 on ShaderBot. I think most areas don't need more than 4, but I'll just go up a little bit just to play it safe. And then for this reflection limits, let's gradually bring this up until we get rid of these black zones. So here's 3, 4, 5, and I'm looking right about here. I want to get rid of these black zones. 6, 7, and we'll say 8. I think by the time we have 8 bounces of specular reflection, we've gotten rid of those black zones as much as we can. So that's what I'd recommend doing. First of all, set your refraction limit to whatever you need. For ShaderBot, I went a little bit above what I think is necessary just to play it safe. And then for the reflection limits, bring that up gradually until you no longer need any more bounces. Let's now focus back to some theory and talk about why it is that light is getting distorted whenever we have a transparent object. So let's say that we have some photons and they hit this object right here. This object has an IOR of 1.5 and the surrounding air, so we'll say the air equals a IOR value of 1. Remember, IOR is referring to how quickly light can pass through a medium. So the higher this IOR value is, the slower light will travel. Now, something interesting happens, and that is whenever we hit this grazing angle, that is when light is going to bend. And so let's say it hits this sphere, it might do something like that. And the best explanation I can give to why light bends like this in the real world is because if we imagine this beam being made up of a bunch of photons, so let's say we have some photons and they're all nice and orderly in a row like this. Well, these photons want to try to keep the same distance away from one another. And so what ends up happening is this. As those photons pass along in this direction, the photons that hit the slow medium first, so let's say the photons on this side, they're going to slow down. And when they slow down, remember, they want to keep the same distance from one another. So what ends up happening is that it takes the group of photons and it begins bending them in that direction. So it's really the force that happens when they all want to stay the same distance away. That force is what causes the photons to bend themselves as they approach this new medium. And then as they reach the other side, then they speed up again. And then that's why it goes back like that. So anyway, that's the best explanation I have for it. There's plenty of free videos if you're curious about this stuff online. So if you go online, look up refraction, look up how that works. There's all kinds of great explanations for it. And for right now, we'll just say that this is why that happens. Also, just as a fun fact, if light hits the medium at a straight angle like this, then it's just going to pass through without bending. So really, it's only the light that occurs at grazing angles. That's the light that ends up getting bent because of the difference in IOR. Doesn't matter what the IOR of the two mediums are when it comes to this bending effect if the light has a straight path. So let's talk about IOR. I've been giving you guys pieces of information as we've gone along, but I haven't really looked at IOR directly yet. So I think now is a great time to do that. The index of refraction, or IOR, describes how quickly the phase velocity of a light wave can travel through a medium when compared to the speed of light in a vacuum. Now, that sounds totally crazy to somebody who doesn't do science. But basically put, we have a light wave, let's say the color red. That color red has a frequency, so, let's say that this is what red looks like. And the IOR describes how quickly this particular wave, this light wave, can travel through a medium. So that's a good way of thinking about it. For 3D artists, the reason why we're even talking about this is because IOR can describe how much light bends when a material is refractive, as we just saw. It can describe how much of the light is being specularly reflected. It can tell you what the accurate color of a pure metal is. It can also provide information on how light rays are attenuated or killed as you approach the grazing angle of a metal. That's a bit more advanced. We're not going to get into that for right now. And the IOR can also give you information needed for determining an accurate dispersion of a translucent material. So what that all means is that as 3D artists, we kind of pick and choose the relevant bits of information here, and we borrow from the world of physics to get all these things. For this course, we'll only talk about how much light is bending, how much light can be specularly reflected, and I'll also show you how you can determine the purely accurate color of a metal towards the very end here. We're not going to pay attention on how to make custom Fresnel curves. We're not going to pay attention to how to find accurate dispersion for the time being. But I do think it's nice to give a basic definition of dispersion so that you know what I'm talking about in general. Dispersion is this. we have a beam of white light. It's going into the prism right here. We know that the prism is going to bend the light because it has a high IOR value. Now, we also know that this white light is made up of red frequencies, like this, that are low frequencies. We have green frequencies, which are slightly higher than red. And then we have blue frequencies that are much like that. Okay, well, we said that the index of refraction describes how quickly the phase velocity of a light wave being the key here, travels through a medium. And so what that means is that the amount of bending that occurs is dependent on the individual light wave that's passing through. And what happens is that as each one of these light waves bends at different amounts, they get separated from one another. So this white light gets broken out into red, green, and blue. And so the reason why we see red up on top right here is because the red frequency, any lower frequency, is going to bend less than something that's at a high frequency like this blue. So that's why it goes red, green, and blue. Now, another interesting thing about this, and this is just a fun fact, is that because the blue light bends more, that's why the oceans are blue. That's why the sky is blue. All we're really seeing is light bending more easily because it's at this blue frequency. So anyway, that is what I'm talking about when we describe dispersion. And we have a setting for this within our shader. With the principled shader, if you turn up dispersion to, let's say, a value of 2, you should begin seeing these rainbow-like effects appear on the surface. Right now, Karma is still being worked on, so I don't think the devs have gotten to implementing this quite yet. But in the future, I'm sure this will be right there. So that is dispersion. Surface priority, I'm going to talk about that very briefly. Most of the time, you don't need to think about that at all. If you go to the help docs, though, there's some really nice diagrams that talk about surface priority. And so if we go, let's say, down here, you can read up all about surface priority if you want to. It might be applicable to your situation. If you have, let's say, like 30 pieces of ice that overlap each other, maybe that's when you want to start thinking about surface priority or something like that. But most of the time, I don't really need to mess with this. And, it shouldn't be a big thing. By the way, here is dispersion. This is actually what it should look like right here. So see how you have these rainbow looking effects happen? It kind of blurs it out too. That is what dispersion should do. It's also a very expensive render calculation, so you have to be careful about using it. But anyway, that's a bit about dispersion and surface priority. I know I mentioned that I'd tell you guys how to make an accurate metal color with the IOR value, but I'll get to that at the very end. For now, let's cover subsurface scattering.